Regression means it is basically refers to predicting a value. Regression means predicting a value. Now, regression analysis can be linear or it can be a non-linear regression. Now, the focus today is linear regression analysis. Okay. So let's understand the further. Now, when we're doing regression analysis, as mentioned in the earlier session, that you have a relation, you are trying to build or find a relationship between a variable, this is an independent variable, and this is a dependent variable. For example, yesterday's example was that this CGPA score of a student and his score in the AMCAT exam. And AMCAT score. So we want to find whether there is any relationship between a CGPA score and the AMCAT. Now, when we have only one independent variable and one dependent variable, then one independent variable and one dependent variable, you generally plot. Okay, we generally plot the dependent variable on y-axis and the independent variable on x-axis. So this is y and now we may have a different plot points that will affect or that will be there. So you will have a data set of what these CGPA students have scored and what their AMCAT score, and you can plot a scatter plot and you may find different points. Now, what we're trying to do, what is this F in case of a regression analysis? So when we have only one independent variable, this F is generally, we are trying to find something called as a best fit line. Trying to find something called as a best fit line. What is best fit line? A best fit line will be a line which passes through majority of the points. A best fit line will be a line which passes through majority of the points that are available from the data set. That are available from. But surely this line will pass through two important points that may or may not be part of the data set. One is y bar and another is x bar. So x bar comma y bar will be a point on this line. What is x bar? X bar is basically mean of x. And what is y bar? Y bar is basically mean of y. Y bar is mean of y. So surely this line will pass through the mean of x and mean of y. Now the question really comes in, when we have y is equal to mx plus c, we want to know whether this is best fit or this is not best fit. Now how do we uh, do this? That is, this is best fit or not best fit. So before going to best fit and not best fit, we'll understand few more aspects of it. So when you have one independent variable like y is equal to mx plus c, only one independent variable, then it is called as simple linear regression. Simple linear regression. Now, suppose the equation that is in the regression analysis, the equation may be of the form y is equal to, let us say, m1 x1 plus m2 x2 plus c. Okay, I'll write the regular equation also here. Y is equal to mx plus c, where c is an intercept. Now, what do we see that? What is m? M is what is change in y for an unit change in x. So it is basically models what is a change in y for an unit change in x. That is what is modeled by m. Now when we have y is equal to m1 plus x1 plus m2 plus x2, this equation, for this equation, the plot is here, and the regression or the predictor line is a straight line. Okay, the straight line. Now, when we have equation of the form m1x1 and m2x2, m1x1 and m2x2, means that the regression is not a line, but rather it is a plane. So this will be a plane because it has now become a two dimension. So it could be a plane. It could be a plane through which you want to have a prediction. So practically, when we are looking at the data sets, this equation will become of the form. This equation will become of the form y is equal to m1x1 plus m2x2 plus m3x3 plus mnxn plus. So practically, when we're talking about the data sets, this is n dimensional. Okay, this is n dimensional. Now, as a human being, we can only imagine up to three dimensions. Okay, we can only imagine up to three dimensions. So it's easy for us to imagine up to y, x1, x2. But practically, it will be m1 x1 plus m2 x2 plus m3 x2 up to mnxn plus c. Now, what is linearity in this case, and what is regression? Linearity means what? You are adding terms, and that's why this is called as linear model. So this is, with the help of this, you are trying to predict. So m is the component with the help of m and c are the component with the help of which you are trying to predict, whereas you are adding different terms, and that's why it becomes linear model. Linear model. Now we are only talking about the linear model. So there are some conditions about the linear model that now I'll mention here, and then we'll understand these concepts clearly. So with the linear model, what is the first requirement? That the dependent variable has to be continuous numeric variable. That is one part. Second important point is that the independent variables, independent variables, independent variables, that is, for example, x1, x2, x3, and xn do not have correlation among them. Do not have correlation among them. That's an assumption, practically not true. We'll come to it. Okay. Do not have correlation. Means what? X1, X2, X3, Xn do not depend on each other. Okay. They do not depend on each other. But in a practical scenario, this is not possible. But all the linear models assume that the independent variables are independent of each other, and they only affect the dependent variable. They only affect the dependent variable. Third aspect is that we need to study we need to study how much is the dependent variable affected by, or association affected by, the independent variable. So to study this, we may try to find the relationship between, let's say, x1 is the first independent variable against y. Similarly, we need to find relationship between x2 and y. Similarly, we need to find whether there exists a relationship between x3, xn, and yn. Y. So if you remember the Titanic data set, which I am continuously demonstrating in the practicals, every time what we do, every time I say that we have to evaluate this feature against the survived, every time I'm saying that we are trying to establish a relation or finding an association between x1 and y. We're trying to find association between a feature like passenger class and the survived. Okay, or gender and survived, age group and survived. So we need to understand whether there is an association or correlation between each independent variable and dependent variable. Now, out of the x1, x2, so let me, okay. So given a data set, the data set may have, let's say, m columns or some k columns, c1, c2, or ck, or let's say them they are the features of the data. Out of these features, there may be a case that you evaluate c1, c2, c3 up to ck, and out of this you find that x1, x2, x3 up to xn, okay, where x1, x2, x3, xn is subset of c1, c2, c3, ck. So let us assume that there are 100 features in the data set. Out of that, you observe that only 23 features are having some correlation with the dependent variable y. Okay, only 23 features are having the correlation. So you will select only 23 features, and that is what you say that these 23 features are statistically significant. Okay, statistically significant. So all the features given in the data set may not be significant, may not be affecting the dependent variable. So how do we find this? So to do this, what is generally done is you find correlation coefficient. Correlation coefficient is also called as Pearson's correlation coefficient. It is also called as Pearson's correlation coefficient. Now this Pearson's correlation coefficient, its value will range between -1 to +1. Okay, value will range between -1 to +1, and it would be. Now let's understand few plots here. How does the Pearson's correlation coefficient really? So let's say this is the first plot, and and the data points are are there on this plot. A lot many data points. Okay. So you have lot many data points, and then you pass if you pass a line through this best fit line, which is passing through maximum point, you may get a line of this fashion. Now, when you have a direct proportion, that is, as x increases, y also increases, then you have a correlation of approximating towards +1. But on the other hand, if you have a correlation of this fashion, okay, correlation of this fashion, where the data points and you fit a line and the line goes somewhere downwards, it passes through this. Then the correlation factor is close to -1. Okay, correlation factor is close to -1. And on the other hand, if you have a spread of the points in such a way that it's very random, trend observed between the spread of then this generally tends towards this correlation generally trend towards 0. Okay, so +1, -1, and 0. Now, let's understand few more aspects of the code. So now, the second assumption was that the independent variables should not be dependent on each other. So if I have a model of the form m1 x1 plus m2 x, okay, m1 x1 plus m2 x2, then plus c, what is expected that I should find some correlation for y against x1, okay, either going towards plus 1 or minus 1, or as well, and at the same time I should also find a correlation against x2 against y, again going towards plus 1 or minus 1. But if I plot x1 against x2, okay, if I plot x1 against x2, my correlation should go towards 0. Okay, it should go towards 0. Now, if the correlation between dependent variable and independent variable is greater than zero point 0.7, correlation is denoted by r. So if it's greater than equal to 0.7, r greater than less than 1, okay, then we say that x1 is a good predictor for y. X1 is a good predictor, or x is in general a good predictor. If the correlation value, and same on the minus side, on the negative side. So 0.7 less than equal to r less than equal to 1, and in between 0.5 less than equal to r less than 0.7, means you estimate that there is a chance, but you require a bit of an investigation to really believe on whether this correlation should be considered for in the linear regression model. And if r is less than 0.5 towards 0, okay, then generally you tend to omit the feature. The same thing we did in Titanic dataset. Okay, where we don't find correlation, we tend to omit it. Now, if you remember, where we are higher correlation, like for example, in the Titanic dataset, age, passenger class, gender, there we did not omitted the features. But for example, features like sibling, parent and children, okay, there we omitted, uh, there we did not find strong correlation. So we went for a derived feature. So investigation is required. More investigation is required. And features like passenger ID, there's no correlation at all, we know, and that's why we omitted the feature. Okay. Now, what do we want as a linear regression models is that if it is y is equal to m1 x1 plus m2 x2 plus c, we want that x1 and x2, if their correlation is found out, their value should come out to be 0 or approximately towards 0. They should not be dependent on each other. But this is practically not possible. Practically not possible. And so, what we can say on this is that though it's an assumption, now when we are going to omit features, that how we are omitted into the Titanic data set, is called as dimensionality reduction. Okay, this is called as dimensionality reduction. So when we are omitting the features, we are doing dimensionality reduction. And dimensionality reduction can be done one of the way, that is using correlation. There is further way called as principal component analysis. Okay? Principal component analysis. Now, okay. So when we have, let us say y is equal to mx plus c, and if I calculate the distribution of x, and if I find this to be this fashion, what do we say? This is mean of x, and there is a spread which is called as variance. Okay, how do we calculate variance? Variance is equal to each xi minus summation square upon n. Okay, so we calculate this variance or deviation. Now, what does this? If this value is very large, then what we say that? We say that there is a higher spread in x variable x, and so x bar may not be a good central tendency feature. Okay. If the sigma value is higher. But if we have a feature of this fashion, okay, if we have a feature of this fashion, then what we can say that this value is smaller, the spread is smaller, and so we can say that the mean is a good measure of central tendency. Now, when we're doing correlation analysis, we're doing exactly same thing between the two variables. Here, when we're doing only standard deviation and variance, we're doing only for one variable. But when we're doing with y is equal to, between x and y, whether we want to find whether how x is related with y or whether x is a good predictor for y, what we want to do, we want to find this value, okay, plus 1, 0 or minus 1, that is called as Pearson's correlation coefficient. What we're actually doing here is we are, so first I'll write the formula so that we can understand. So what we're trying to do here is we're writing a formula that is xi minus x bar yi minus y bar divided by under root xi minus x bar square and under root yi minus y bar square. Okay, so this r is basically a unitless value. Okay, it's a ratio. So you can look at here. You are squaring the term and taking the square root. So if x is in kgs, okay, and let's say y is in some grams for some reason, then this this will be kg upon under root of kg square. So this root will get cancelled. So this will become kg upon kg, and this will become unitless. So for x it will be unitless. Similarly for y it will be unitless. So r is basically a ratio, and the values in between plus 1, 2, minus 1, and 0. Let us understand what we're trying to do with this. How I have already drawn 3 graphs. Now let's understand the meaning of the graphs. Okay, how do these graphs of correlation really work? Now let us say, let us draw a graph again of some x against y. Now what we have some mean value of x and we have some mean value of y. And there will be a cross section. So this is y bar and this is x. Sorry, this is. Now whatever is your line of regression analysis, that has to pass through this point. We are sure that the regression line will pass through this point, x bar and y bar. Now, if you look at this system, this diagram is having 4 quadrants. Okay, this diagram is having 4 quadrants. When the center of the quadrant is assumed to be at a point x bar dot y bar. Okay, there are 4 quadrants. Now, as there are 4 quadrants, this will be a positive area quadrant. So what we're doing actually here in this case is y the value comes to be plus 1 or y value comes to be minus 1 or y value comes to be 0. So if my correlation is positive, I'll have majority of my points in this area, okay, and in this area. Okay. So actually in terms of quadrant, what I'm trying to do is I'm taking area of this part. So here my ideal y bar value will be negative. Okay. Here my x bar value will be negative. Negative with respect to what? X and y value will be negative with respect to what? With respect to x bar as the center of the coordinate system. And so negative area will become positive. And on this side, my x value will be positive and my y value will be positive. So if my majority of the points fall in this quadrant with respect to x bar and y bar and in this quadrant, both the areas are positive and so this will move towards 1. Okay. As against if my covariance, so covariance means what? So if I take again the same thing, this is x bar and this is y bar for the next graph. If my majority of points fall in this quadrant, this will be positive, this will be negative, and this will be negative, and this will be positive. So here the areas would be negative. Here also the areas would be negative, and so negatives, that's why it will go to, okay, it will go towards minus 1. And approximate towards 1. So if I want this correlation to be 0, means if the correlation is to be 0, what is the meaning of this? Is again x bar, y bar, and my data points are evenly spread in all these 4 quadrants around the mean. Okay, my data points are evenly spread around this corner, around this coordinate system. And so what will happen is that these will be 2 negative areas and these will be 2 positive areas. So summation of positive and negative will give it to me a value closer to 0. Practically. Ideally, if the points are uniformly distributed, this will be equal to 0. This will be equal to 1, minus 1. This will be plus 1. Okay. That is how you look at the correlation factor or coefficient. So, so when we're talking about this, what practically, as mentioned earlier, what practically happens is when you have a regression line going through this, there could be points which are away from the line. There could be points which are away from the line. And then what we tend to do, what does this say? And let's assume that the mean is, I'm considering minimum points. So this is x bar and this is y bar. Okay, this is x bar and y bar. So now what does this say? That for this point, let us say for this point, okay, so observed value of this point is here. Okay, so this is the observed value y, actual y, and actually what happens, this is the predicted value, means what your model says that for this x value, let's name it as x1. For this x1 value, the observed value is y, but the predicted value is y predict. And there is a x bar and y bar. So this is x bar and this is y bar. Now if you look at this, what is the expected thing? That the expected value of y is y bar, but your model says it is not y bar, it is yp. Okay. So you have a gap at this point. Okay. You have a gap at this point. And what is another aspect that we are looking at here is your model says that a predicted value of y is this on the line, but your observed value is here. So there's again one more gap here. Now this is called as regression error. Okay, this gap is called as regression error, wherein this gap is called as residual error. So yesterday I had mentioned some concept of residual error. And residual error. And the total gap, that is from y to y bar, is called as total error. Okay, so this is total error. So this total error is basically residual error. Okay, residual error plus the regression error. Okay, the regression. Now, why this differentiation? The regression error is the error which is captured by your model. So this is captured. The model knows it. Okay, it has explained it that your prediction is along this yellow line, the slanting yellow line, and you expected the value to be on the horizontal y bar line. But there's a gap between the two that is captured, and that's why it's called as regression error. Wherein a residual error means the line could not pass through the observed point, rather it passed through another point. Okay? That is a residual error, and your model is unable to explain this. Okay, and that's what is called as residual. So the model at this point in time is unable to explain this error, and that's what is called as the residual error. And what is residual error? Residual error is square of y minus y predicted summation upon n. So that's the total residual error. So if you remember the variance formula, so this residual error is also variance or variation. What is that variation? It's the variation of the predicted value and the observed value. So this error, the residual error called is nothing but it's a variance again. The formula is very similar to variance, or is exactly similar to variance, but it's not called as variance. It's called as the error, residual error, but it is variance of the observed value and the predicted value by the model. The observed value and the predicted value of the model. This error is also called as sum of square errors. Sum of square errors. Why sum of square? Because you are squaring the error first and then you are taking the summation of it. That is also called as sum of square errors. So any doubt? What we're trying to do here is we are trying to evaluate the against error against various possible lines, and we are trying to find a global minima inside this convex shape or convex functions. So this and the line which gives us the error value approximating to 0, and then corresponding m value and c value will be treated as a best fit value, and that is what the regression algorithm does. So in case of programming the regression algorithms, what happens here is that how fast your algorithm comes to this bottom, how fast the algorithm comes to the minima, that is global minima, that is defined or controlled by something called as alpha, which is the learning rate. The learning rate. Now, alpha value of too small alpha value will say that this global minima would be reached very, very gradually. Reach it very, very gradually. And alpha value of too high will say that you'll reach this global minima in a haphazard way. That is, you may be at this point, okay, and second time you may directly jump to this point because of the learning rate. Then again you may jump here, and again you may jump here, jump here. So you may move into a haphazard fashion when the learning rate alpha is high. So learning rate is also called as the rate at which the algorithm learns. Smaller the learning rate, the gradient descent will move gradually towards the global minima. Will move gradually towards the global minima. It will take large amount of time for learning the algorithm. So number of iterations could be more. So alpha small, the iterations could be more. Alpha bigger, it will jump haphazardly to the global minimum.